Hey everyone, my name is Jason Gauchi and I'm going to be talking to you about soft body dynamics using Verillet integration. So what we have here is a wheel simulated by some soft body dynamics. You could use this to simulate cloth or really sponge or any kind of soft body. And we see is that it's made up of a series of particles and constraints. So each of these lines is a spring constraint. And where all these lines intersect here at these intersection points, those are particles that are being affected both by the constraints, by gravity, and then also by this rotational inertia here to simulate a wheel. The way this works is that the particle's position is updated through something called Verillet integration, which I'll talk about briefly. This is an example of parabolic motion of something moving through space, like a baseball flying through the air or something like that. It goes up for a while, it reaches its apex, and then it starts descending. This is where you get that 9.8 meters per second squared acceleration. And usually someone would use Euler integration, which looks something like this. So you compute the velocity and you compute the position based on the delta over time of the one above it. So for example, if I'm at time 0, I compute the velocity based on the acceleration. In this case, I'll start off with some initial velocity to give it some boost, plus the negative acceleration, compute a new velocity, and then move x along that velocity. So it looks something like this. So now, the problem with this is that it looks very different from this parabola right here. And what's happened is we've used this equation to estimate the new position at this new time, but we kept velocity constant when really velocity was changing. This is just an artifact of the way integration works, any integration. But it's especially noticeable with Euler integration. Now eventually this will sort of converge in a sense that it will start to look like this. And then right at this point you've reached almost the apex of the curve, so your velocity is going to be roughly 0. And it'll kind of come out like this. And then it'll start to descend. But what you'll end up with is a lot of air. There's another integration method that's a little bit more robust called Verillet integration that follows this equation. Essentially you need the current and the previous position. So rather than the Euler equation that uses the position and the velocity, the Verillet equation uses two positions and the acceleration. In this case the acceleration is constant. It's not changing over time like the velocity is. So there will still be inaccuracies because you're doing a numerical integration. But the idea is that the accuracies would be much reduced and it would look something like this. So it produces a result that's a little bit more stable. Another nice artifact of this is that you can stick to just using the positions. In fact, the velocity calculation is only for your information if you want to use it to do some additional processing. You don't even really need it. So I could simply take that wheel as I was doing and move it around on the screen just by changing its positions and not have to worry about what the velocity is. So I hope you guys enjoyed that. You can download the source code and also a demo of the executable. Another interesting thing that you can do with this demo is you can change the number of particles. So for example, you can make the particles 40, and what you'll see now is that it looks a little bit more like a real wheel. Now this is going slow because this code hasn't particularly been optimized, and it's written to kind of be more informative than performance oriented. But now we can see that this is sort of moving more as we would expect, and it's a little bit more robust to the collisions that it's experiencing.